Hello everyone, we're going to talk about one of the most badass and underrated features of TypeScript that could really level up your game as a TypeScript developer. The feature I'm talking about is TypeScript Generics. Before we begin, we have to ask ourselves, what are generics? Well, generics are a type of variable used to capture the types passed into different components or functions. Think of them as a way to tell a function or a component what types of data it should expect and return. We're going to take a look at 3 code examples that uses TypeScript generics, a basic example, an intermediate example, and finally a more advanced use case with TypeScript generics. We will also be taking a look at the code examples without the use of generics, just to get a better understanding of the value that generics bring to the table. First, let's take a look at a basic example of a TypeScript generic function. Before we start, I'd like to shamelessly plug my YouTube channel, so if you find this tutorial useful in any way, please leave a sub to the channel and hit that bell notification icon to get notified of new videos. Thanks. So here we have a basic example of a generic function. We have a function called identity, which just takes in an arg and then just returns the arg. Simple as that, right? But you'll notice here that we've added some things to it to make it a generic function. So we've added this thing in angle brackets, and this is called a type variable. And the type variable allows the user of this function to specify types to pass in that we can use in our code. So you can see here that we are indicating that this identity function takes in a type t with the angle bracket. That's usually how you determine if this function is a generic function, because it has these angle brackets. That's usually the rule of thumb here. So we take in the type t, and then we define that the argument is of type t, and then just the value as the type t. Now it's called t, but it doesn't necessarily have to be called t. It can be called anything as long as it's assigned in the right places of the generic function. Like in this case, the parameter of the argument arg, which is here, and the return type, which is here. So we can name this generic anything. We can name it type here, or we can name it anything. As long as it's assigned in the right places, this function will still work. Now, the reason why we're doing generics is because when we create this function, we don't really know what types are getting passed in. And we're going to talk about constraints with generics later, but here is just a basic example of what a generic function looks like. You can see that we're calling the identity function here, and we're passing in the argument myString, which is a string type. And when we hover over the output string variable, you'll notice that it preserves these types. And that is the magic of generics, right? Because if you were to use something like an any type, which we would take a look at later, this would have been assigned to an any type. So you can see that we are able to preserve the types using generic functions. Same thing with this identity call here, where we're providing a number which is 100 to the arguments of this identity function. And when we hover over the output number, we are able to determine that the return value is the number 100. Now here we have the exact same function, except we're calling it differently. It's now called identity nodegenerics, but it functions the exact same way where it returns the argument. But here we're not using generics in any way. We're just providing the any type as the type of the argument, and then the return type would also be an any type. Now, when we use this function, we no longer have type safety. In fact, it ruins type safety for basically everyone, right? So if we take a look at this function, identity nodegenerics takes in an arg of type any and returns a type any, even though we know it's a string. When we hover over this variable, it's now an any type. So it doesn't preserve the types, which is absolutely terrible, right? So same thing here, identity nodegenerics. We're using the same function, and you can see here that output number nodegenerics is now an any type. So we lose the type safety, even though our function is very simple. So you can see the value of what generics brings to the table. We are able to enforce type safety and have our function be flexible for many use cases, making our code more reusable and at the same time predictable. Now, one thing we can do is to create static types for the arguments and the result values of this identity function. You will notice here that I have created a type, identity statically typed input, which is a union of a string and number type, and another type called identity statically typed result, which is also a union type of string and number. And we define those as the arguments instead of using generics. But there's actually a drawback to this. One of the drawbacks is you have to maintain the type. So for each type you think your function will support, you sort of need to maintain this identity statically typed input as well as the result type, right? So it's not as efficient. And one of the things you actually lose is because this is a union type, now the return value or the result value is actually vague. If we hover over the output string statically typed variable, it is inferred as the identity statically typed result. And if we try to do some operations on that variable, dot, and you can see that these methods that are available to us are methods that the string and number type have, but not individually. If we go back to our example and we try to do some operations on the output string variable here, we can actually do all of the methods that are available to us for the string type, and the same thing with number types. And remember, the value of TypeScript is that we are able to determine issues in our code at compile time rather than runtime. So using generics instead of this approach would be more efficient and more maintainable, as well as not ruin type safety for everyone. Here we have a more intermediate example of using generics. So you can see here we're creating a generic interface called API response, which takes in a generic type T. Like I said, you can name this to anything, type, or basically anything at all. So what we're doing here is we're defining the structure of the interface we know about, right? So we define that the API response always has a status of number and always has a message string, but we don't know what the data type will be. So that's why we're sort of assigning it as a type T, since we don't know about it yet. So here we have an example of constructing a variable using this generic interface. So we have here let user response of type API response, and then we're passing in the name and age as the generic type. So what it would look like would be status 200, which we've defined here in our API response, message success, which is also a string, but the data now has name and age, right? Name string and age number, which we have indicated here. Same thing with product response, right? So you can see here that we have created a variable called product response, which is of type API response. We then provide a type that it's an array string here to our generic interface. And now we can compose an object that looks like this: status 200, message success, and the data would be an array of strings, which is apple, banana, and cherry. So generics are widely used in library code. An example of this would be using Axios. Everyone knows about Axios. It's pretty much everywhere when you're making requests to API endpoints and other things. So here we're doing an axios.get, but you can see if you hover this, right? Let me remove the types that we've passed in here first. You will see that this axios.get is actually a generic function. And the way you know if it's generic is because you see these square brackets here. So that's usually how you know. So we're going to add those types back in. We know that when we make the get request that the result or the data object would have the property name, which is a string, and age, which is a number. Now, usually if you navigate to result.data in Axios and you don't provide the types, which we're going to do here, let's just remove this. And if we do dot, you will notice that the properties of data is unknown, right? And that's because we didn't specify a type for the generic. So now let's specify name and age again. And if we go to result.data and we do dot, we can see that we have the age and number properties available to us in data since we've defined it here. So now let's take a look at a more advanced use case with generics. So it would look something like this. So let's take it line by line for us to better understand what's happening here. So here we have a class called store. Here, this is the class, which we can assign a generic type to, which is here. You can see that we have class store, square bracket, t extends, id, and number, right? You'll notice that this generic type has the extends keyword. Now, what does that mean? So you remember a while ago in the basics example where I mentioned we talk about using constraints in generics? This is exactly what I was talking about. So here, what t extends id number means is basically we can pass in any type, but that type must have a property named id, and that id must be of type number. Pretty cool, right? So we're able to place constraints on our generic components just so the code would work as expected. You can imagine if we remove this constraint of ID and number, and when we run this get item by ID, where item needs to have an ID type, then this code will just throw an error because the ID property wouldn't exist and we couldn't do this logic. So this store class, everything's fairly basic. We have a items array here of type T, add item to add an item. We just push to the array and then get item by ID. So this is where placing constraints on our generics becomes useful because we sort of need whatever type we're passing here to have the property ID and it must be a number. Otherwise, this code wouldn't work. So it's still flexible, right? But it has a few constraints, specifically just one, to make sure our code works just fine. So here, in terms of using it, we define a type, which is product. It must have the properties ID number, which is the constraint we're placing on this generic, a name string, and a price, which is a number. So we're defining a product store by instantiating this class, new store, passing in the product, and we're just basically using those methods. And then there are no TypeScript errors here. So if we remove this ID number property from this product type, that's when TypeScript throws an error. So like I said, right, throws an error, type product does not satisfy the constraint, ID number. That's pretty legit. That's so cool. Yeah, so it's always so mind-blowing whenever I have to witness anything with generics. So it's pretty cool, but you can see here that before we even run the code, TypeScript lets us know that our code is incorrect. And that is because of the constraints we placed on this generic, right? It must have ID number. So we're going to place that back in, but that is an advanced example of how we could use generics with our code.